Hello there, all our graph fanatics. Thanks for joining us for this week's online meetup. We do have, sorry, I have a video up on another screen and it's like playing on top of myself. I hear myself. Thanks for joining us this week. We have something special for you. We actually have two of my favorite colleagues in the London office. That's where you guys are, correct?
Yeah, good. You narrowed it down a bit.
So before we get started and go through all the information about what's happening, maybe we could just introduce you guys. We could start off there. So yeah. Mark and Irfan, would you like to tell us about who you are and what you do for Neo and how you got here?
Yeah, I'm Irfan. I am in the team Bloom currently, and we are developing the recently released essay Bloom, Neo4j Bloom, which is a graph visualization and data exploration tool that we with a part of actually a graph platform.
Yeah, and okay, cool. My name's Mark. So I work in the developer relations team with Karine, and I'm mostly sort of basically trying to make it easier for developers to integrate Neo4j with whatever tools and other products that they're using. And so the stuff we're going to be presenting today is something that Irfan and I have been working on for the last couple of months.
How did you guys get started on working on this project?
Yeah, so I guess maybe to get to there, that's kind of the beginning of the presentation. So maybe
okay, so I won't go there yet. I'm just going to say
okay,
really quick window. If you're watching live, there's a live chat window on the right-hand side of the YouTube video. You can ask questions there directly, and I will awkwardly interrupt the conversation and ask Irfan and Mark the questions that you guys have. Also, if you are interested in presenting in the future for any of other online meetups, you can post about your project in our community site. If you are not watching this live and you have questions for the presenters, for Mark and Irfan, we also have a link to the community site thread about this project. So if you have questions there, you can always ask them after the fact. And set your resolutions for 720 megapixel on the right-hand side of the bottom of the screen. And I think that's it.
Yeah, cool. So let me present from our side.
Oh, and thumbs up if you like the talk.
Cool. So yeah, I guess you can set me as the presenter.
Yeah.
Or maybe I can. Cool. All right. Okay, so let's have a talk about what we're going to talk about today. So we're going to kind of have a look at sort of two different things. So we're looking at graph analytics and graph algorithms, and how that collides with the Game of Thrones world. So that's the plan. I tried to find a picture of Irfan where we were smiling on a Google, but unfortunately he looks really, really serious. So you get a serious picture of Irfan on there. But this is the agenda. So we're going to, I guess some of you may have attended some previous talks, or perhaps you've seen some presentations by our colleagues Michael Hunger or Amy Hodler, where they've talked about the graph algorithms with Neo4j before. So we're not going to do like a super long introduction to that, because there are other talks, and we can Irfan actually has the YouTube live stream on his screen, so we can we'll share some of those with you if you've never seen this before. So we'll just do a brief intro to that. Then we're going to show you the tool that we've been building, which allows you to run graph algorithms on Neo4j while not having to write any code, which I think is quite a compelling thing for a lot of users. We're then we'll go into Game of Thrones land, and we're going to be looking at how do we apply graph algorithms to that data set. Although, of course, if you're in Neo4j land, we call it the Graph of Thrones rather than the Network of Thrones. And then probably about half the talk is our plan. So probably first half an hour sort of introducing stuff, and I hope, well, depending how quickly I talk, it could be less. And then we want to spend most of the presentation sort of showing you how you can use this tool, and we'll obviously share the instructions for how you can use it as well. Okay, but back to the beginning. So, quick refresher for you if you've never watched any graph algorithms talk, or you've maybe come across it but don't remember exactly what's going on for a while. So, graph algorithms kind of comes under this category of of graph analytics. And so graph analytics is just the idea of I'm doing some analysis of connected data, and I can use any graph-based approach. And the one you may be most familiar with is sort of what we've categorized as graph pattern-based querying. And so this is more the stuff you see like kind of in transactional type workflows where you're doing local data analysis. So perhaps I'm doing some sort of query around a particular person in a graph, and I'm trying to find all the information in their neighborhood. And typically, Neo4j users would be doing that using the Cypher query language. So just writing some Cypher queries, maybe it's some simple patterns in there. And then on the right-hand side of this diagram, we have graph computational algorithms. And so here the goal is still to analyze our data, but we have a slightly different approach. So here we might be wanting to like analyze global data, so like analyze the whole graph. And we might want to be using an iterative approach. Like a lot of the algorithms, graph algorithms are iterative in nature. And Cypher is a declarative language. So we typically just say, hey, Cypher engine, go and execute this query. And we can't express iterative logic in there. And so that's the reason why we need a slightly different approach than what we have for our graph pattern-based querying. So what I want to do next is just quickly go through, okay, so what sort of things can you do with this new tool? And so there are kind of falls under three kind of problem areas. So one of them is related to is often in routing or pathfinding. It's can we do some planning? So maybe if it was like planning a train route, maybe it's like, hey, can you find me the quickest way of going between two stations? Or on this example here, maybe we're modeling some IT network infrastructure, and we're trying to find, okay, what's my cheapest path of using this this infrastructure to execute a task. Then we've got another area which can allow us to find like central nodes or important nodes in a graph. So this diagram here shows a US airline data set, and we're trying to work out, okay, what are the important hubs in this in the US flight network, and those are shown on this diagram as bigger circles or bigger nodes. And the idea is, can we figure out, okay, how are failures likely to cascade? Like where are the problematic places where we maybe don't have much redundancy in our network? And then the last one is kind of quite interesting as well. And this is, can we find bridge points? Can we detect communities in graphs? So this is an example of the Louvain algorithm, and it's trying to detect amongst some phone calls that are happening between people. Can we find clusters of the people who are talking to each other? And the colors here are indicating which language people are talking. So in green, it's one language in Belgium, in red, it's a different language. And the one on the bottom right-hand side where it's mixed is people who are able to talk in both languages. And so these algorithms can find this type of structure without you don't really have to tell them what the structure is. They can kind of go and find it from the graph. And this leads us to the general idea that structure can hide, and we might not necessarily be able to find it just by executing a Cypher query where we tell it exactly what we're trying to find. And so these algorithms, and they have different characteristics, are able to sometimes find a structure, like, hey, find me a community that I didn't know existed, or hey, find me a path, find me a best path that I can't actually see just by manually inspecting the data, or can you tell me which are the important nodes when I maybe can't see just from the properties that those nodes have on their own? So it's effectively, from this graph structure, these algorithms help us go and find, hey, what structure, what parts of the graph are important that maybe I can't tell just by some pattern-based query. So that's the high-level overview, and hopefully it gives you an idea of the types of problems that we can address here. So how do we use it in Neo4j? So we've had the Neo4j Graph Algorithms library since, I think it was about July 2017 was the first release of this. And we've had it available on the Neo4j docs page since probably about July 2018. So a lot of the credit for the work on this page goes to our colleague David Oliver, who works in the documentation team. So he's kind of structured all this and made my English actually sound readable. So thanks to David for that. But then our next question people have is, how do I install this? So it doesn't come with Neo4j out the box, but it's not super hard to get it installed. So if you're using the Neo4j desktops, if you're using this on your laptop, and we'll be showing an example of this later on, you just go to your plugins tab at the top, hit the plugins tab, and then on the right-hand side we've got, you can see, probably you're familiar with APOC already. So there's another one here called Graph Algorithms. So we just hit install and restart. and then we're done. Or as our Prime Minister would say, simples. Right, so moving on. So what is in this? And once we've installed it, what do we got to play with? So like I said, there's 3 types of algorithms. We've got centrality algorithms. So these are for determining importance of nodes in a network or in a graph. We've got pathfinding. So this is like, can we find like an optimal way of traversing our way through a graph structure? Or perhaps evaluating whether a route's available and the quality of the route. And then we've got community detection, which is, can we find out how a bit of data is clustered or partitioned? So I'm just going to do a quick dive over what is available in each of those categories. So we'll start with pathfinding. So we do single source, shortest path. We do all nodes, basically all pairs, shortest path. We've got BFS and DFS. Those are actually used by a lot of the other algorithms, and they are now implemented as procedures in their own right, and will be in the next version that's released. And then a new one that we added probably in the last 6 or 7 months was one where you can find not only the shortest path, but hey, can you show me the K shortest path? So show me the shortest path and the next shortest path and then the next shortest path after that, which can be quite useful if you're trying to work out, okay, if like my shortest path is not available, what's my next best one? So that's pathfinding. We've then got centralities. So we've got obviously the Google made famous, the PageRank algorithm. We've also recently implemented a couple of variants on that. So we've got the article rank and eigenvector centrality, which are kind of quite similar in some ways to PageRank. And we'll explain when we get to the examples how they differ. But we've also got between centrality, closeness centrality, and degree centrality, which again, you could do degree centrality directly in Cypher, but we've implemented a parallel version that you can run from the Graph Algorithms library. And then finally, we've got the community detection algorithms. So the most commonly one that people are interested in this category is the Louvain algorithm, but we've also got label propagation, union find or weakly connected components. We've got strongly connected components, and then we've got triangle counting. And each of these have like a slight variant of the problem that they're very useful. That they kind of solve in their own unique way, I guess. So we're not going to go into detail about all of this because there's other talks that do it. But I just wanted to quickly show you. So if you were like, okay, cool, I really like this library, or maybe you've already downloaded it, and you're like, okay, so how do I use it right now? So what you would have to do is you call these as Cypher procedures. So we're still able to use the nice Cypher query language that we're familiar with, and we've just got this extra call clause that we execute our algorithm with. And each of the algorithms has 2 variants. We have the streaming variant, so algo.name.stream, and we have a non-streaming version as well, so just algo.name. And we pass in a configuration. So it's at the simplest, it's a label, so a node label, followed by a relationship type, and then you can pass in some configuration. And this can be used to control hyperparameters of each of the algorithms, or it can just be used to control, hey, what concurrency do you want to run out? What property do you want to write the result to? So if you want to do it now, this is your approach, and it's not super hard, but it doesn't mean that you have to write some code. So you need to be reasonably familiar with Cypher, which leads me to the topic of this meetup. So I'll let Irfan take over for this next section.
So what is Neuler? It's basically a graph app that runs within Neo4j desktop. It provides a user interface on top of the existing Graph Algorithms library. So then you'd have to use Neo4j browser or any other like Bolt that requires some knowledge of Cypher.
Yeah, and again, so maybe we can explain like what a graph app is in case somebody hasn't seen it.
Oh yeah, so as if you're not aware, Neo4j is providing a Neo4j desktop that is basically an entrance to the graph world, let's say, so that you can easily access lots of applications that you will make use of power of graph applications, including Neo4j browser, Neo4j ETL, and Neo4j Bloom. You can create databases, run them, manage them with a cool user interfaces, and so on. And Neuler is one of these recently. It's a part of actually Graph Lab, which is still under development and the early beta phase. But we would like to share this with you since we know that there are lots of inquiries for this. So it runs on top of Graph Algorithms. It uses procedures provided by Graph Algorithms plugin of Neo4j.
Yeah, and then basically like the UI is written completely in React, right? So we built that.
Yes. Yeah, this is of course a JavaScript-based application. It's React-based.
And it feeds in, so you're able to, like, from the desktop, it feeds in your credentials, and it just runs on whatever your active database is. Right?
Yes, that's a good thing that Neo4j Desktop provides. You don't have to worry about connecting anywhere. So whichever your database you're connected, you're in. You don't have to worry about that.
And then the goal is.
Yeah. So as you have just processing, you need some level of Cypher to be able to run this stuff. And also, even though you know that, for instance, let's say you're using Neo4j browser. Neo4j browser is a generic tool that is optimized for representing any kind of graph output, Cypher output, whereas Neuler is optimized and going to optimize for providing good UI UX that helps you interpret algorithm outputs, specifically that's shipped with graph algorithms.
Yeah. And then I guess, yeah, just to reiterate what Irfan was saying. So this is like a beta product, and it's not like I guess similar to our Halen meetup. This is like an application that is supported by our developer relations team, rather than being like an official Neo4j product. So I guess maybe let's show people a bit of a look at it. So we've created some print screens for it. So this is treat this as version 1. This is our first attempt at what we think is a useful way of interacting with these algorithms. So we're gonna show you how to use this for real, but it's easier for us to just quickly explain to you how it works. This is a print screen of what you get when you launch it. So you can see here we've got on the left-hand side. So we're currently supporting 2 of the algorithms. So we've got also 2 of the types of algorithms. So we've got centralities and we've got community detection. So you can see that over in the left-hand side.
Hey, Mark, really quick question. I have somebody in the community. They asked if you can actually define what the context of community detection means, like what it's actually based on. So I don't know if you're getting to that now or not.
Yeah, so we can. Yeah, so for community detection, each of the algorithms has a slightly different approach, but they're effectively trying to find communities of nodes based on the structure in some way. And there are different. I guess Irfan is going to share a link to the documentation, but each of them has like a different definition of what a community means. So if I just pick like a simplest example, the strongly connected components example, for example, strongly connected components, it assumes that 2 nodes are in the same community or in the same partition, or sometimes you'll see it referred to as the same set, if there's a relationship in both directions between those nodes. If there's not, then you're in a different partition or a different set. Whereas if you take something like label propagation or the Louvain algorithm, they have a slightly more fuzzy definition. So it can be actually not even deterministic. Sometimes, depending on the order at which nodes are evaluated, you can end up with a different result.
Great, thank you.
Yeah, so the best, like for the really, really accurate answer for each one, it's best to look at those documentation page that Irfan's just shared. So anyway, so back to here. So we've got support for 2 of the categories. And then once you click on one of them, for example, here we've clicked on centralities, it zooms in and it shows you the individual algorithms for each one. And so, for example, here we click on degree, centrality, and it will take us to this little box here, or this little form. And the idea is this form is kind of simulating what you would have to type into the Cypher query, right? So,
yeah, definitely.
So on the top, we've got the top level specification. So what do you want to run this algorithm against? Like what label or what relationship type? Right now we have support for that specification. We haven't made support for typing in Cypher queries. You can actually type in Cypher queries here as well. We haven't made support for that because we assume like the initial use case for it is actually, okay, I've got a graph that I can actually run it on, and actually the whole intention was not to write any Cypher. Yeah. So for version 1, we've gone with that. Then if you go down to the next row just below that, you can define, okay, what direction of graph do you want to run this on? And what this means is, if you say I want to use the out degree, it would be like, it only considers relationships from going out from a node in the algorithm. If you say in, it's only relationships coming in. And if you say both, it treats the relationships as if they're bidirectional. So in Neo4j, all relationships have a direction, but you can choose to ignore that direction if you like. And then you can see there are a few other properties as well. And then the idea is if I went to change it to PageRank, PageRank comes in place of that degree, and then we can run that one instead. And once you've run it, you get this pane on the right-hand side, which gives you the results. So you get a table view of the results, you get a visualization of the results, you can see a chart of the results, and you can also see what code it was if you want to go and run it yourself. Anything else to add on there?
No, I think that's pretty much brief.
Cool. All right. Okay, so next question. How do I install it? So since Neo4j Desktop 1.1.14, I believe it is, there is a one-click way of doing this. So Irfan is going to paste this link in here, but if you've got Neo4j Desktop installed already, this link here will automatically install Neuler for you onto your Neo4j desktop. As far as I can tell, this works on Windows and it works on the Mac. It doesn't work on Ubuntu. So if you're using Ubuntu, you need to do a slightly different approach. It's just a couple of extra clicks. But you need to go on your Neo4j desktop, click on this little 4 squares icon, and then where it's in the bottom of the screen says install graph application, just paste in bit.ly install Neuler. And then that will achieve the same thing as what the previous link is doing. And Irfan will post that as well. Okay. So that leads us to our data set. So our plan now for the rest of the next half an hour or so is to explain how to use this on the graph of threads. Now, just in case you've not somehow managed to miss the fact that there is a new season of Game of Thrones coming up in, I guess it's in about a month's time. So we decided to quickly go downstairs and get you a picture. This is from outside our office, just under the bridge of next to our office. So clearly London has gone a bit Game of Thrones crazy, and I presume there's something similar to this in other countries as well. But this is one of the adverts for the UK TV version of this. And there's actually a nice data set. So this is an example of a clustering algorithm applied on this Game of Thrones data set. And the data set itself is not invented by us. It comes from a Professor Andrew Beveridge. And you can see on the bottom right-hand side of here, and we'll paste this link for you also. You can see that he's done like a lot of analysis on this data. And so I'm just going to go over to there so we can just have a look at what he's been doing. But yeah, the credit for this data set and this idea is all comes to here. So this is the website. So it's a network of thrones. And originally, he started by analyzing the novels. So you can see here, like there's so much information on here. It's a feast if you like looking at graph algorithms or network science, and if you like Game of Thrones. If you've never seen Game of Thrones, this website is the perfect way to completely spoil it for yourself. So keep that in mind. But previous to about 3 months ago, there had only been data for the novels available, and so you kind of had to kind of work out, okay, in that book, which part of the book like maps to which season that I've seen on the TV. So I seriously don't have the patience to read those books. I imagine they're way too long for me. So I've only seen the TV series. So I was doing the analysis on the books, and I was like, oh, this doesn't really map with what I've seen on the TV. And I was like, oh yeah, but it's not actually the same as what's on the TV. So actually, like more recently, he's posted up the data for the TV series. So this makes our life much easier. I see we've got a question. Is there a graph database for this? We're going to share that when we get to the next section. So he's made available this data, and he's also done some analysis on it as well. So we're going to focus on season 2, just because this one seems like the most interesting from an analytics perspective. But Andrew Beveridge basically does like a walkthrough. He gives like a high level. So this is like a clustering algorithm. I didn't realize our screen was going to be so much Strata adverts. So apparently there you go. This is Strata conference.
Pay us, right?
Doing some free advertising there. And then he does like an explanation of what is going on, just for like kind of explains what happened in this season just from looking at the output of these structures. And so he does community structures and also does centrality measures. And so our goal, like what we said, when we were organizing this meetup a couple of weeks ago, I basically said, do you think we can replicate his post? That was the goal. So this is our plan. Can we come up with something like this
By
using
Neuler?
Yeah, exactly. So I want to just quickly show you the data. So he shares the data on the website. So kind of up here, you've got this data section. So we're going to look at this Game of Thrones one. So I've actually made a fork of it because I wanted, the naming was a bit inconsistent for what I wanted to do in the import script, which I'll share in a second. But effectively, what he's done, so he explains here, maybe I zoom this in a little bit, how the graph works. So it's a really simple graph. And if you search for Game of Thrones graphs, there are some really complicated ones there that capture like people killing each other, people changing allegiances, where people have been in different episodes, like the family relationships between people. There's all sorts of stuff. This particular data set is really, really simple. And it's just literally, did people interact with each other or not? And he has a kind of explains like a mini algorithm for how do I know whether they interact with each other, explained in these 5 steps. It's like, did they speak directly after each other? Did they speak about someone? Did they speak to each other? Did they appear in a scene together? And he generates these CSV files. So let's just have a quick look at one of them. So the edges files are a bit more interesting. So let's see whether this is going to do it. So this is what you get. So you get a source node and a target node. So these are representing people. The order doesn't matter. Remember, this graph is undirected. If Cersei spoke to Tyrion, that means Tyrion, or Cersei interacted with Tyrion, that means Tyrion interacted with Cersei. The weight is how many times they interacted. So the higher, then that should be the better. So it means that the relationship is kind of stronger. And then the season is kind of superfluous in here because we've got in the title as well. And you can see it's available for all 7 seasons. I just did a little bit of renaming so that it fitted into an automated script. So what I want to show you now is how do we get this data in the database. So I'm not going to spend like really long on this. So I'm just going to tab over to my Neo4j browser. So you can see here, this is what maybe I'll zoom it in a little bit again. This is the overview of the database. You can see it's very simple. We've got at the node label level, we've just got characters. And so we can click on that. We can see which characters we've got. So you can see here we've got a load of characters. And if we double click on one of them, probably not a great one to pick there, but you can see it shows the interactions between Daenerys and all the other characters. And we've created one relationship type per season that the characters interacted with. So basically, if 2 characters interacted in season 1, we see a graph a little bit like this. So these are all the interactions that happened between, or 25 of the interactions that happened in season 1. I'll just show you just quickly the script. So we're using this is the import script. So if you want to grab this script, we've actually put it on the community site link. I think we might have put that at the top, or at least. So it's about 5 from the top. So if you want to grab this script, you can see it on there. It's reasonably simple. So we're basically just iterating seasons 1 to 7, and then we're creating nodes for the characters, and then we're linking them together. If you want to run this script, you need to make sure you got APOC installed at all as well. Sorry. The reason for that is because we want to build a dynamic relationship type based on the season, and you can't do that directly in Cypher. So that's the reason for that. And we're also, in case you want to paste it, make sure you turn on your multi-statement query editor. So you can see on this little cog tab, it's the second one of the checkboxes. And then that will allow you to paste it in, and you'll have the same database as we have. Okay, so that's the data set. I guess we're probably now ready to show you how to do some analysis. So let's just quickly remind ourselves, what are we going to try and do? So if we go to season 2 of Andrew Beveridge's blog. So we're going to start with the centralities. So if I just zoom this in a little bit. So this is what Andrew Beveridge has done. So he's got degree centrality, he's got weighted degree centrality, eigenvector centrality, PageRank, and betweenness. So these are the 5 that we're gonna try and emulate, and we're going to talk through what we're doing at each stage. So if we come over to the Neo4j desktop, if I just show you what would it look like if we didn't have it installed. So you can go. So I'll select my Game of Thrones project. So this is how my project looks like. I've got way too many projects, but it's a nice feature that was recently added to the Neo4j desktop is it highlights your active one. So this is my one down here. So online meetup. You need to make sure that you have that Graph Algorithms plugin installed. I believe in a future version of the Graph apps, we'll be able to specify that as a precondition of the app. But right now, you need to make sure you manually do it. we do have a
internal check for that.
yeah. So if you don't have it, it will tell you, hey, you need to install this. But from future, it will automatically install it for you. If we come back, I guess, again to here, once you've added that application, you will see it available here, and it's version 0.1.8. So it's Graph Algorithms Playground. And if you click on it, you'll end up on this screen here. So you can see we're ready for degree centrality. And remember, we want to do season 2, right? So in this case, we don't need to specify label, but let's specify one anyway. So we say, I want to run it on characters. Then we need to choose, OK, what season are we going to use? So we can choose any of the seasons, but since we said season 2, let's pick season 2. And usually we thought for degree centrality, like what it computes is basically like, how important am I by direct connections to me? So how important is a node based on direct connections? And so we've defaulted this to use incoming relationships. So we were thinking, like, what would you most likely use this for? It's probably like, hey, if I'm trying to find out if someone's important on Twitter, like, or directly important, maybe I'm going to count how many followers do they have. So it's kind of an incoming relationship. But in this case, it's actually both, right? So it's just number of interactions. Who interacts the most? So we pick that. You can then say, hey, do you want to store the results? So we'll say yes. We'll leave that. By default, it will store it for us. And we're going to store it as the degree property. So let's run that. So if we run that, you can see we get back here. It gives us this table view. So we can see just by, so this is like based on the number of characters that are, a number of people that a character interacted with in season 2. Geoffrey comes to the top of this list. You see he's got a score of 36. By default, we're showing the top 20. You can control that over here. So if we say, hey, I want to do 25. Oh, I messed it up now. So we go back to 20. So if we want to set it to 25, if we run it again, you see we get a few more people on the end instead of just, maybe I just hide this icon. So you can see we can get the top 25 people that we have available in terms of, or top 26. I've got a bit far. So that's how you run it. So that gives us like the individual unique characters. But what happens if we want to like count it up? Like say I only interacted with a few people, but I interacted with them a lot, and we want to give some credibility to that. So what we need to do there is we need to go to our weight property, and we need to type in weight. So this is the name of the property for that.
So for clearance, this property already exists in the relationship. Is it
Yeah.
Cool.
Yeah. So so I guess maybe the next version we can make this a drop down and pick only the relationship properties that are available. But for now we have it available like this. So if we run that, it slightly changes the order, I think, at the top. So you can see now Tyrion is top with a score of 960. You can actually go and just check, compare it if we want. So just check, okay, so this one was Geoffrey. So Geoffrey interacted with 36 individual people, but his total interactions was 425. So he was not interacting as much. So basically, Tyrion was talking a lot, but to less people. Okay, so that's degree centrality. We can also, I guess the next thing is, so that's the table view. We can also have a look at a chart view if we want to see like a relatively, like you can see here, like this much more clearly than I was able to see on that table. Tyrion has interacted almost more than the next two people combined.
Yeah, that's the interpretation, right? You can immediately see ratios as well, just not just the numbers. Well, I mean.
Yeah, so we can do a chart view, and then we could actually go and compare that to the previous view as well. So we can see this is the chart of degree centrality, and then that was the chart when we were showing less people, right? So this is the top 20, this is top 25, and so you can kind of like, it's quite easy to go and compare. Hey, I want to have a look at what I just ran, compared to what I've just done now. So that's our first algorithm. Now we're going to look, and we can check. We can quickly check. Do we see similar results? So Geoffrey was top on the first one with 36. Second was Tyrion with like, I don't know, a little bit less than 30 or so. And then if we look at weighted degree, top should be Tyrion, 960. So we got the same result there. And then Cersei should be second, and Geoffrey had fourth. Was he down to fourth? So he's down to fifth. So we should be seeing, so that is what we see on here. So we can see Geoffrey's down to fifth. On the blog post, we don't have the exact answers. We just know what is the top one. So we're kind of like, okay, well, I guess that's good. It's using the same data. So we should be seeing the same result. But obviously, this is a super simple and embarrassingly parallel algorithms, so you would hope this is going to be reasonably easy for us to do. Now we're going to look at a little bit more complicated one. So this is eigenvector centrality, and this differs slightly in that from degree centrality. So we're still trying to find important people, but this time rather than importance being only on the direct relationships to a node, we're considering like transitive relationships. So as Irfan was describing it, in this data set, it means that we're finding people who interact with important people.
Yeah.
Right. So we should hope to see people who are like transitively important come up here. This one, so PageRank does a similar thing to this as well. The idea here is that you specify a number of iterations, and on each iteration, the node is kind of distributing a little bit of its score to its neighbors. With eigenvector centrality, on each iteration, the node gives all of its score to its neighbors. So if I have like a score of 10 and I have 3 neighbors, I give all of them 10. We'll explain, we'll reiterate this when we get to PageRank, but for PageRank, if I had 3 neighbors and a score of 10, I give each of them 10 divided by 3. So it kind of like almost like dampens my influence. So like if I'm connected to loads of people, the PageRank kind of dampens my importance, but the eigenvector doesn't take that into account. So they're kind of useful for slightly different things. So if we run that again, we're gonna get some scores. Our default for this one is to show just the raw score. So after each iteration, we do a normalization of the score, and then we continue with the next iteration. But by default, we're not normalizing it at the end. We thought this was quite a nice one, though, for showing the visualization tab. So we'll just click over to here for a second. So this is using a tool that our colleague Will created called Neo4j. So we at the moment, so the code for this app at the moment we've got it is closed source, but we will be open sourcing it. But at the moment we've got this all in line because there was some stuff we wanted to do directly in here, and it was easier if it was all in the same code base. But this is effectively Neo4j, and you can see here we can sort of hover over the nodes, and it's basically showing us the nodes and all the relationships that they have between each other. You can see there are some really small ones over here. The nice thing you can do on here is we can actually change it. So if we decided that, like even on this view here, we could say, hey, show me the degree centrality results, and it will refresh the chart. So now we get like a slightly different view. Slightly different people are bigger. So you can see Tyrion is the main one on here. You can see down here is Aria. At the moment, the reason they're all the same color is because is node color. At the moment, we just said it uses the eigenvector centrality, which doesn't really make much sense. That node color property will only make sense once we get to our community detection algorithms, which will be there in a minute. But we wanted to show you, finally, one thing we found was helpful while we were debugging it. Basically, while we were finding errors that I made, or copy-paste errors that I made, was we made this code view as well. So if you want to check or debug or repeat yourself, you can actually just take the code in here and paste it into your Neo4j browser, and it will run that. For you. So the top bit is just parameters. So you set a whole load of parameters, and then the second one is the query to run. We're going to run that. We'll show you how to run one of those, but I think it's more interesting. We'll do it on the PageRank example. So let's come across to here. So for PageRank, remember this is slightly different. It's a similar concept as eigenvector centrality. Actually, no, I forgot one more thing. So if we want to, for eigenvector centrality, if we want to directly reproduce what Andrew Beveridge has on the blog post, so remember that he's got his number, sorry, I scrolled a bit fast. His top number for eigenvector centrality is 1, and ours is way higher, right? So it's 93. The reason for this is normalization. And it's a normalization technique called max normalization. So if we do this, we get the same results as him. So it's basically what it does is take all the scores and assume the top score and divide everything by the top score. So the top score will be 1, and everything else is relative to that. You can also do other variants of that. So we can say, hey, I want to do an L1 normalization. This one is kind of everything needs to add up to 1. And you can see it just slightly changes the config section. So you see we get this extra normalization parameter in here, and then the eigenvector centrality's third argument is the config, and it will read that and go, okay, I need to normalize it. And the normalizing happens, it doesn't happen in Neuler, it happens on the algorithm side. Cool. So let's go back to PageRank now. So if we come back to PageRank, so remember this one is similar to eigenvector centrality, but instead of the nodes giving their score to everybody. They're kind of dampening it before they give it to everybody. So we get a slightly different result. So we run it here. So this is on the non-weighted one. So this is purely on interactions. So you get Joffrey at the top. Probably if we want to match what Andrew Beveridge has done, we need to add in the weight. So we need to do weighted PageRank. So now we get Tyrion, Aria, Daenerys. And so that's what we're seeing on here. So Tyrion, Aria, Daenerys is in third. Yeah. And again, we haven't actually got this in our PageRank algorithm, but we're gonna add it as well. On this one, is actually done a different normalization. So this is the L1 normalization where everything needs to add up to 1. But on the eigenvector one, it's done max normalization where the top one is 1. I'm not sure why there's a slight difference. The algorithms that Andrew Beveridge is using are in Gephi, the client-side visualization tool. Different libraries seem to do different things. So we've tried out everything on here on Network X. And Network X uses actually even another type of normalization called L2 normalization, where it takes every result, calculates like the square root of the sum of the squares, and then divides everything by this result. So we have that for eigenvector centrality, and we'll bring it across the PageRank as well. I guess the last thing we wanted to show was between the centrality. So this one is different again. So this is like if the way that people interact is based on the shortest path of the path between the two characters, which nodes are kind of really central to that communication. So again, let's do season 2, since that's what Andrew Beveridge has done. And this time we just want to show you the streaming version of the algorithm. So by default, we're storing the result on the nodes. But what we want to do here is actually just stream the result straight back to the user. I guess maybe to explain, which I didn't before, was in Neuler, when we do the store version, we're actually in the background running a Cypher query to get the results back. With the stream one, it doesn't store anything. It just sort of runs it and sends the results back to us again. So on this one, we get top is Aria. So Aria is actually central to the communication network, or like the shortest path communication network in season 2. And you can see it with a score of 12, 27. Maybe easier to see on here. But it would be quite easy. We could say, hey, show me season 4. So we could run that. So you can see here, a higher score kind of means that those people are basically they're more central, whereas a lower score kind of means it's more spread out and there's not people who are so central across the piece. The code view here obviously now uses a different algorithm. So we can maybe just quickly show how does this one work. So if we just copy this, we come over to our Neo4j browser, we can paste this in. So those are the properties, and then if I go here, let's copy the query. And so you can see the same. You can see the same results in the browser. And this is basically what Neuler is doing. It's not super complicated. It's basically like simplifying the creation of the specification that you run the algorithm, and it's running it for you, and it's showing the results in a bit more of a easy to process way. That's what we're doing here. Okay, so last thing to look at is the community detection algorithm. So if we move down, so this is just the second tab down here. So we're going to run the Louvain clustering algorithm over this dataset. The Louvain algorithm is what we call a modularity. It's a modularity-based algorithm, and the idea here is that nodes get put into a cluster, and the cluster will have, or they start in like their own cluster, and then they move around based on whether or not the modularity score increases from moving them. And the modularity score is determined. There are different formulas for this, but it's roughly based, like at a high level, it's based on how many connections do I have inside the cluster and how many do I have outside. And then it checks, okay, if I move you from one cluster to another one, does that improve the score? And so it's basically trying to find out, okay, where's the maximum modularity? And it's using an approximation algorithm. The actual perfect modularity is like a really it's like a really long time to compute. So we tend to end up with one which is an approximation. So again, let's put the weight property in here, and let's run this algorithm. Again, note it's storing the property on the Louvain. It's the property that it will store on is Louvain. But
so this is the actual place where the table list doesn't help much.
Yeah.
Where we would like use visualization for this.
So if we tab over to here.
So yeah. Okay, so here we can clearly see the community in season C, where if you look at zoom here, where if you could remember Daenerys, all locked up in this far world of Khal Drogo on their own. So they are kind of like a distinct community, clearly to be seen here. And
yeah, because they were off, right? They didn't interact with anybody
else
in all the rest of the lab.
So you can just see it at once with this algorithm, which is very good. And also one thing to here, we just recently added actually. Now current node size is also Louvain, which actually doesn't make much sense. We are using color for community, which is good, but we can also use our output of other algorithms here. For instance, PageRank, so we can see at once both the importance of people as well the communities they belong to.
Yeah, so if we go over to the Daenerys community, you can see, as you would expect,
yeah,
Daenerys is the most important one. Whereas if we come over, say, to the red one that we see over here, Theon is the most important. And what is interesting here is that now that we can actually, like, although we ran Louvain, we can show anything, right? This is completely configurable. So we could say, hey, I want to run like season 7. So run me this for season 7. So if we run for season 7, and then show me the graph for season 7, and maybe we do the size again, PageRank. We'll just use the. I guess the season is a bit weird. Like you can go slightly crazy. So you could say season 2 PageRank with season 7 clusters. Yeah. So you end up with this structure. So you can see now everybody in season 7, everybody's one happy connected graph. I don't think there's anyone disconnected in this one.
Oh, things get hot here.
Yeah, but there's a lot of you see everybody's kind of overlapping in the middle. So yeah, I guess that's what we wanted to show you. So maybe we come across quickly to the slides again to wrap up. So do give this a try. I guess this is like our first attempt to show this to somebody who's not one of our colleagues. So if you give it a try and you have some ideas or feedback or something you don't like or something you want added, you can post this on the community page. So maybe we can post this again on the bottom of the chat. But yeah, basically, just to conclude, I mean, we've shared the links for you already. If you're interested in this topic in general, we have a graph algorithms book that I've been working on with my colleague Amy, where we sort of go into a lot more detail on each of these algorithms that we've shown. And I've put a link on this slide here. So if you go to this link, you can register and you'll be notified when you can grab a copy of this book. And I guess for now, maybe we hand back to Karine, and then if there are anything else any questions we need to answer.
Okay, thank you guys so much. I really appreciate you guys taking the time out to present to everyone. Let's see, I think that Irfan, between you and Irfan, I think you guys answered a lot of the questions that were asked. David Mesa said, great job, looks very interesting, and he's looking forward to giving it a try.
Cool. Yeah, let us know how you get on.
Awesome. Yeah, because the video is a little delayed when I went with the actual live streaming questions. And then Irfan said thank you. He's on the chat.
Yeah,
no problem.
And I think that's it. I think that most of the questions have already been answered throughout the talk, so I think we're good. If anybody does have any other questions and you're not watching live, feel free to go to the community site. And I did post it in the chat, but we're also going to post it inside of the description for the YouTube channel.
Cool.
And that's it.
Yeah, and if you like the talk, don't forget to like it as well. So shameless so that other people can find the video.
Yes, definitely. So make sure you give the video a thumbs up. All right, thank you, everyone.
Cool, thanks.
Bye.
Thanks, bye.